Oh boys, I tell you this is pretty hardcore for me, seriously. So this thing right here is not trivial, not even in the least bit. Good morning, fellow mathematicians, welcome back to another video. This thing right here is going to be pretty hardcore. We already made 3 prerequisite videos just to prove one simple theorem. I didn't want to use Stirling's formula for this theorem, and that's why I'm taking the really difficult route right here. And you see, I've seen many constructed proofs. So proofs where you actually have to construct yourself something that works out nicely, but this thing right here tops it all. So whoever came up with this proof is an absolute mad lad. My highest respect. This is just absolutely ridiculous. Gauss multiplication formula is today's topic, and we are going to prove it using all tools we have derived before. It's pretty hardcore, but keep watching, it's really worth it, it's pretty crazy. So the first thing that we actually have discovered is that we can basically express this ratio of gamma functions as nothing but this product right here. More formally, you would call this thing right here a Pochhammer symbol or an ascending or descending factorial, okay? So that's the more formal terminology for what we did right here, and also we have calculated 2 quintessential limits, those right here, and also this really neat trigonometric formula right here, so that one was pretty cool in my opinion. And what we are going to do is we are going to manipulate this whole expression right here into something that we can actually work with, okay? So what I would like to do at first is to bring all the stuff that has an n in it to one side and the other stuff to the other side, okay? So what actually has an n in it? So this has an n in it, okay? And we can divide both sides by k to the nk power. We want k to be fixed at the moment. It's just a fixed integer, for example. So we can divide both sides by it. It's not equal to 0. And also we can drag this pi notation to the numerator and denominator and divide by this product on both sides. Also, I would like to multiply both sides by gamma of k times t. Okay, that's something we can do to arrive at. Okay, so it has to do with a lot of manipulations right here. This video has actually been requested, so I only looked into this thing right here because someone actually requested me to do this right here. So what do we get? We're going to get gamma of k times t plus n times k. Okay, then we are going to get over k to the nk power, and then this pi notation as being equal to 1 to k, and then gamma of t plus n plus s minus 1 over k. This right here is actually the first part, and then the second side of the medal is that we are going to multiply both sides by gamma of k times t. Okay, so on the other side we have, I'm going to put it like this, gamma of k times t over this pi notation right here. Okay, I have to do a lot of thinking right here because this is pretty hardcore of a proof, so in my opinion it is. I want you guys to acknowledge something. This side right here is pretty constant when it comes to taking a limit with respect to n, okay? So if we would, for example, take the limit as n approaches infinity on both sides, then this thing right here is just a thing itself, so taking a limit of a constant is just a constant itself, but we still have to take the limit on this side. So what I would like to do is to take the limit as n approaches infinity on both sides. I'm going to regard this limit to as nothing but capital L, okay? As always, we are going to write it as a capital L. Meaning, now for the big chalkboard, we are going to get that gamma of k times t over this pi notation thingy, gamma of t plus s minus 1 over k is nothing but the limit as n approaches infinity of, okay, gamma of k times t plus n times k over k to the n-kth power times, and I'm going to put it like this, pi notation of the rest. Okay, 1 over, and then we are going to get gamma of n plus t plus s minus 1 over k. I'm terribly sorry, my leg was itching. I don't know what it was, maybe an insect, I don't know. So this is what we have right here at the moment. This in itself already looks pretty terrible. Now we want to make use of the limits we have shown before to be equal to 1. Okay, so what we want to do, we want to multiply this argument of the limit by a 1. But what is a 1? Well, a 1 is nothing but this over this times this chunk over this chunk. Okay, those are both 1s, and we can multiply by 1s, it's okay. So that's going to be a pretty terrible expression now. So that's actually equal to the limit as n approaches infinity of this chunk, gamma k times t plus n times k. Now you maybe understand why I made several videos on that, okay? K to the n-kth power. And then we are actually going to go for this thing right here at first. So we are going to multiply it by kn minus 1 factorial n times k to the k times tth power over the same thing, k times n minus 1 factorial n times k to the k times tth power. And then what we are going to do, we are going to go into this pi notation right here, into this finite product. And what we are going to do, we are going to multiply this 1 over gamma function by nothing but this chunk over this chunk. Okay, so bear with me here. By n minus 1 factorial n to the t plus s minus 1 over k. Okay, over the same thing, n minus 1 factorial n to the t plus s minus 1 over k times this thing right here. Okay, it's a lot of work, right here. 1 over gamma n plus t plus s minus 1 over k. But we already came pretty far. We have done a lot of prerequisites, we have done a lot of work already, so this thing basically falls from the sky. And like I said, this right here is a pretty hardcore constructed proof. So everything in here is constructed so nicely that it actually works out, and it's pretty amazing in my opinion. Whoever came up with this, chapeau, my boy. So you see, now we can take the limits separately. Under the condition that those limits actually exist, we can collect terms and take the limits right here. So what do we actually get? We get that gamma of this chunk in the limit is nothing but 1, meaning this is nothing but we are going to get rid of this thing right here, and we are going to get rid of this thing and also this thing right here. So all that's really left is this part. Okay, what else do we have? We can track the limit to the inside on all of those terms separately, and we are going to get rid of all of this chunk. So getting rid of our gamma function and also this numerator right here. All that's really left at the moment is the limit as n approaches infinity. You see, this is Arabic right here for limit. Oh boy. K times n minus 1 factorial n times k to the k times tth power over k to the n-kth power, pi notation from 1 to k of, okay, we are going to have 1 over n minus 1 factorial n to the t, and I'm going to put it differently, plus s over k minus 1 over kth power. Okay, for reasons that will become apparent in a second. You see, if we have n to the a plus bth power, this is the same as n to the a times n to the p, meaning we can break this up into n to the tth power times n to the s over k power times n to the negative 1 over kth power. Why is this important right here at this point? Well, if we take the finite product of those parts, for example, this 1 over n minus 1 factorial is actually kind of glued to this expression right here. So if we take the product from 1 to 3, we are actually going to multiply this expression 3 times by itself, but with this s changing in a different way all the time, depending on the member of this product right here. Meaning, we are going to get, for example, 1 over n minus 1 factorial 3 times to the third power, meaning this thing, if we drag it to the outside, is actually to the kth power. Then we are also getting this n minus 1 over kth power right here to the kth power once again, leaving us with n to the negative 1th power. Same thing here, n to the k times t. Okay, I'm going to bring this to the outside, and all that's really left is the product of this chunk right here. We're going to see what it is in a second, okay? So this is the limit as n approaches infinity of k times n minus 1 factorial n times k to the k times t power over k to the n times kth power. Then, like I said, we are going to drag stuff to the outside. 1 over n minus 1 factorial to the kth power. That's a lot of factorial right here, okay? And then we are going to get n to the t times k power. And I want you guys to notice that we have the same thing right here. That's supposed to be a t, and then you can immediately see that this and that is going to cancel out, okay? So that's good. And also we are going to get 1 over n to the negative 1th power is nothing but n in the numerator right here, times this product s being equal to 1 to k of, and if we take the reciprocal of this thing right here, that's nothing but n to the negative s over k. I don't have any space left. This right here is pretty exhausting for me, but we are halfway done, okay? So the hardest part is basically done, and we are going to concentrate on this thing right here, and I want you guys to remember the function equation in the real and complex numbers when it comes to powers. Okay, so I'm giving you a second, I'll be right back. Bruh. We are going to continue. Like I said, I wanted you guys to remember the function equation in the real and complex numbers regarding powers, okay, with the same base. If you multiply n to the 8th power and n to the bth power together, bth, YouTube drama, n to the bth power, we are going to end up with n to the a plus bth power, meaning if we have a finite product right here, or an infinite product, it depends on the convergence of this thing, we can actually bring this product up here into the power as a summation, okay? So this is just the thing I said, just with k arguments this time, instead of just a and b, which are 2. Meaning this thing overall is nothing but n to the negative 1 over k. I'm going to put it like this, times the summation from s being equal to 1 to k, so that's a finity boy, a finite boy of s. If I let k go to infinity, this is going to weigh to negative 1 over 12. That was so bad. If you don't do this, then you're actually going to end up with little Gauss. We have used this before, if I remember correctly, on this one. If you don't know what it is, then you are completely wrong on this channel. Get the fuck out, seriously. You have no deal with this channel right here. So we are doing way harder stuff on here. So this is actually going to end up with, okay, little Gauss tells us that this is nothing but s. No, I made a mistake. I'm stupid. I'm not suited for being on this channel. Ciao. No, obviously just kidding. We have to get this video through. So this thing right here is actually going to end up with k times k plus 1 over 2, and you can make this clear by choosing a little example. So if we take the sum from 1 to 3, okay, this is 1 plus 2 plus 3, giving you 6. But what is 6 exactly? It's nothing but 3 times 3 plus 1, which is 4, so this makes 12 over 2, 6. Hooray, works out wonders. Okay, so this power up here is nothing but negative 1 over k times this chunk. You see k and 1 over k is going to cancel out to being nothing but n to the negative k plus 1 over 2. Okay, so if we write this out, we are going to end up with, on this side, the limit as n approaches infinity of k times n minus 1 factorial k to the k times tth power over k to the n times k times n minus 1 factorial to the kth power. Okay, we got rid of a lot of stuff. This thing right here is nothing but n. Okay, but what else do we have? We are going to have n to the, I'm going to put it like this, negative k over 2, negative 1. If we multiply this and that together, this is n to the first power. So this is going to be n to the negative k over 2 minus 1 plus 1th power. So this and that is actually going to cancel out. What actually have we gathered, right? This was over 2, I'm terribly sorry, negative 1/2. So if we add 1 to this thing, we are going to get positive 1/2. I'm terribly sorry. What did I think right here? That was so stupid. I can't even distribute stuff into something. Okay, never mind. What actually have we gathered right here? So we now know that this thing, which is constant, okay, is equal to this chunk. Here's one cool thing. All those terms are actually dependent on n, and we are going to take the limit as n approaches infinity, except for one term, k to the k times t power, okay? And this is why we introduce those limits, just to extract this little boy from all of this. So why not divide both sides by k to the k times t power? Okay, going to get rid of that. It's not equal to 0. Now, this is still independent of n. This right here is dependent on n, meaning all of this work just for extracting this term right here. If we still take the limit as n approaches infinity on both sides, this term is constant. This one is constant, okay? This is just going to evaluate to some real number, which is basically this limit right here. So this limit has a solution. This weird term has a solution. And it becomes clear that it really has a solution because this term right here is growing really hard. You are going to have a factorial to the kth power, okay? So this thing right here is growing really hard, meaning it's kind of descending. It's going to converge to some value, okay? So overall, what we have gathered after doing all this stuff is that this in itself is constant, okay? All this work just to see that this thing is indeed constant, okay? Just because this term is not dependent on n. So this thing is basically just a function in t, okay? We're going to call this constant, for example, we could call it kappa, but then you would mistake it for my k, so we are going to call it z, for example. Our goal now is to find out what c actually is, okay? This is our main boy for now, and we are going to dive right in. Meaning, what we can do, we can change our k right now, because this k is kind of not too nice at the moment. So that's something that's bothering me right here at this moment, okay? Because that's kind of a function in two variables right now. So why not choose k such that a lot of stuff would cancel out, okay? For example, why not choose k as being 1 over t right here? Because then we would get gamma of 1, which is nothing but 0. Also, we would have, for example, this 1 over t just here, because we have 1 over t times t is just to the first power. Okay, I hope you can see this. Now, this is going to imply if we make a change of variable, for example t being equal to 1 over k, that's equivalent to saying k is nothing but 1 over t, we are going to get, okay, gamma of 1 is nothing but 0 factorial is 1, okay? So this constant is equal to 1 over. What do we have right here? This is going to give us, okay, this is going to evaluate to nothing but 1 over this t is nothing but 1 over k, giving us k to the first power, which is nothing but k. I'm terribly sorry, I had to think about what I'm doing here. We are going to get rid of the t, not the k, so it doesn't matter, it's the same procedure no matter where you start right now, okay? Then we are going to have a product running from s being equal to 1 to k of gamma of 1 over k plus s over k minus 1 over k. 1 over k is going to cancel out, so this is just gamma of s over k. Like I said, I'm terribly sorry, I have to think about everything I do here. And also it's so warm in Germany at the moment, it's like 32 degrees Celsius out there, and I'm sweating like an ugly fucking pig, okay? So we have gathered this. What we can do, we can multiply both sides by k, for example, to get Kelvin Klein on this side being equal to this chunk. Now we can take the reciprocal on both sides. Nothing is equal to 0 right here, okay? We don't know what the limit is, but we don't want it to be equal to 0. We are assuming that it's just some fixed constant right now. So 1 over Kelvin Klein, Ck, is nothing but this pi notation from 1 to k of gamma of s over k. Now, if you write those terms out, something different becomes clear. So the last member of this thing is actually gamma of k over k, meaning this is nothing but gamma of 1, it's just 1. So we can get rid of this. So reduce this upper index by 1, okay, up until k minus 1. Also, what we can do, if you write those out, multiplication is abelian on the real numbers. We can actually invert the order of taking the product right here. This also becomes clear if we say that let some new variable or let s be equal to u minus k. It's the same procedure right here. Okay, this is our new running index, meaning that s is going to run from that u is going to run from, okay, we have to solve for u right here. U is nothing but s plus k, meaning this is going to run from k plus 1. In this case, u is going to run from k plus 1. Let me think for a second right here. No, k minus u, I'm terribly sorry. This wouldn't make any sense otherwise. Okay, k minus u in this case. That's why I said it really doesn't make a difference what we substitute in here. So that's also equivalent to saying that u is nothing but k minus s. Okay, now we can make a shoe out of this. Okay, now if we plug s into here, our product is actually going to run from u being equal to k minus 1. And if we let it run to k minus 1, we are actually going to get 1. Okay, and this is going to result in gamma of k minus u over k. How does this help? Well, like I said, this pi notation is abelian, meaning we can actually interchange those upper and lower bounds, because just write out the terms, shift them, and then you are going to get the very same product just with the index shifted. So we can actually write this as, and I'm going to bring this index back to s, okay, as s being equal to 1 to k minus 1, okay, running over the same index, that's already good, of gamma of k minus s over k. And I want you guys to notice k minus s over k is nothing but 1 minus s over k. And maybe you can already see this magic happen right here. Okay, now what we can do, we can actually multiply 1 over Kelvin Klein with itself. Okay, so this is 1 over c squared k squared. But what is this exactly? Well, on the one hand we know that this is nothing but this, on the other hand we know that this is nothing but this, meaning we can actually multiply this by this. We have a product running over the same index, so we can collect the pi notation right here. Just take a piece of paper to write out for yourself, it does work out. So from s being equal to 1 to k minus 1 of gamma of s over k, and this thing right here is the most satisfying thing ever right now. Okay, gamma of 1 minus s over k. And we know what this is. This is nothing but Euler's reflection formula. Like I said, this is the most satisfying thing ever. This right here is actually nothing but pi over the sine of pi times s over k. Link will be in the description to this video. Whew. Isn't that fucking dope? Because now we actually have a product over this thing. That's why we have derived this before. Meaning all that's really left to do is to drag our pi to the outside, just the same argumentation as before. We are going to take the product of pi with itself k minus 1 times. Meaning we can divide both sides by pi to the k minus 1. Okay, that's not equal to 0. So that's equivalent to saying 1 over c squared, k squared, pi to the k minus 1 is nothing but this pi notation once again of 1 over sine pi s over k. And now we can just take the reciprocal on both sides, apply this theorem that we have derived before, and then we basically have our c right here extracted from it. We are close to being done. Bear with me for a second longer. Okay? Okay? I'm giving my best here, my boys. Now, we are basically done with everything, like I said. Don't forget, k is fixed, meaning we can cancel out a k on both sides. We don't want it to be equal to 0. So let's just get rid of this. Also, we're going to divide both sides by k times pi to the k minus 1 power. And I want you guys to notice that pi and 2 are going to have the same power, meaning we can just bring those together, multiply them and extract the power, okay? Meaning overall, that's equivalent to saying that c squared, I'm going to put it like this for now, it's nothing but 1 over k times 2 pi to the k minus 1 power. Now what happens if we take the square root? Because taking the square root is the last thing we actually have to do. Well, in normal case you would get a positive and a negative branch, but I've written it here. I want you guys to notice that the gamma function in the positive reals, for example, is strictly positive all the time, and also k to the something, it's a fixed positive integer, for example, is also positive, meaning our constant is bound to being positive, meaning we can raise both sides to the 1/2 power, take the positive branch, leaving us with c being nothing but. Okay, I'm going to put it like this. This 1 over something power is just all of this to the negative 1 power, so k to the negative 1/2 power. Then we are going to get 2 pi to the negative. Okay, I'm going to put it like this for now, k minus 1 over 2 power. And this right here is our c, my boys. Meaning we can plug it into here. This is nothing but k to the negative 1/2 power. Then we are going to get 2 pi. And now I'm going to do what I wanted to do. I'm going to distribute negative sign into here. So 1 minus k over 2 power. All that's left for us to arrive at Gauss multiplication theorem is to multiply both sides by this chunk right here. Okay, basically, is that all we really have to do? I'm thinking, it's a multiplication formula, so we are going to multiply both sides just by this, and we are going to divide both sides by this right here, leaving us with nothing's equal to 0. This weird multiplication. If you write all those terms out, you are going to get, okay, then this is nothing but gamma of t times gamma of t plus 1 over k, blah, 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 up until t plus k minus 1 over k, okay, gamma of this chunk, being equal to, okay. Now, this is 1 over k to the k times t power, so that's k to the negative k times t power. I'm going to start here with this gamma of k times t. Okay, I could have just not distribute this negative sign here, never mind. Okay, we are just going to reverse what we did right here. We are going to divide both sides by this chunk, meaning we are going to get k to the 1/2 minus k times t power, okay? And the last thing is nothing but to get our 2 times pi to the k minus 1 over 2 right here. Yeah, and this is it. It's as easy as it is, okay? It's pretty trivial. This right here is Gauss multiplication formula. Like I said, this is an absolute hardcore thing, and I was so afraid of making this video because I just thought I couldn't film this because it's just so ridiculous. And as always, I'm doing everything without my notes here, so that makes it even harder. I thank you guys for watching. If you did enjoy this video, please like, subscribe, and recommend the channel if you like. I hope everything I did in this video was indeed correct. If you want to support the channel, buy those t-shirts I created, support channel on Patreon, blah blah blah, you know what you can do. And up until the next video, have a gamma multiplication day, whatever. See ya, that was pretty exhausting. Ciao. Oh, wahrlich zu spät.